Hello. Today we will be talking about titrations. So let's start this off. Waiting. So typically, one of the first things that we would do in a titration is a standardization. What a standardization is, how should I write this? To pick a compound to titrate an unknown compound. This standard is essentially has to be a known concentration. Which is determined through a process known as standardization. So in this example that we're going to use, we are going to standardize KMNO4 with Na2C2O. So the idea here is we are going to prepare a solution of KMNO4 at what we think is a known concentration, and then we are going to react it with Na2C2O4 to determine the exact concentration of that KMNO4. So the reaction proceeds as follows. We have 5C2O4 will react with 2MnO4. And notice how I am not including the potassium and the sodium from these because they're technically not participating in this reaction. This is going to also have some hydrogen ions through, this is going to be done in a slightly acidic solution. And this will produce 10 CO2 plus 2 Mn plus 8 H2O. So this is the reaction that's going on between the KMNO4 and Na2C2O4. We need to know the reaction in order to determine the ratio of the two compounds. So see C2O4 and we have MnO4 here. So for every 5 KMNO or for every 5 Na2C2O4, we will have 2 KMNO4 reacting. That's essentially the ratio that we need here from this reaction. So let's set this up. Let's say that I were to use 0.3562 grams of Na2C2O4. OneNote is having a graphical problem. That fixes. Right? All right, so let's say we have 0.3562 grams of Na2C2O2 in 250 milliliters H2O. So let's say 48.36 milliliters of KMNO4 hydrant reacted with 10 milliliters of a solution containing the Na2 O4. What is concentration of KMNO4? So let's try to draw a picture of what just happened right here. So I took a volumetric flask, and let's say this is a 250 ml volumetric flask, and to it I added 0.3562 grams of Na2C2O4. So I added that to this flask right here. Let's see, what did I do next? I then essentially mixed this up, and I took into an Erlenmeyer ten milliliters. So I put 10 milliliters of this stuff into here. I then took this with my burette, KMNO4. And I used 48.36 milliliters of that. Based on this, we need to figure out the concentration of this KMNO4. And the idea is we take the Na2C2O4, we find the initial concentration of the solution that we just prepared in this 250 milliliter volumetric. We then take an aliquot of that solution, 10 milliliters of it, to put it in this Erlenmeyer flask. We then use the idea of what is molarity, is moles over liters, to determine the amount of moles of Na2C2O4 are inside here. Then we take a reaction that goes on between the KMnO4 and the Na2C2O4, and using the ratio and the volume, we determine the moles of, or not really the volume yet, we determine the moles of KMnO4, and then we divide that by the volume of KMnO4 to determine the concentration of KMnO4. And at this point, we would say that we have standardized the KMnO4. Technically speaking, we'd probably perform this 3 times to take an average. So let us go through the math involved in solving this. So let's start out with writing 0.3562 grams of Na2 C2O4. We're going to multiply this by the molar mass of Na2CO2O4 to determine how many moles we have. Typically speaking, this is usually always the first step that we do. We are then going to multiply it by 1 divided by the volume. And this is essentially, we're going from grams to moles, moles to molarity. So we now have 0.0106 molarity. So this is the concentration that is in the solution that we initially prepared. But remember, we are essentially taking a portion of that solution and using it for our titration. So, to finish this off, we will say that 0.01063 molar of this C2O4. And just so I note for you guys, is it? The Na2C2O4 and C2O4 I am essentially interchanging around here, but it technically doesn't matter. Honestly, C2O4 is the species that is being reacted, so technically speaking, we don't need to include the Na2. Sometimes I'm including the Na2, for instance, for this to determine the molar mass and whatnot. But so we now have this C2O4, 0.1063 molar of it specifically. And what we will do is we will multiply it by 0.0010 liters. What this is going to do is, remember, moles, molarity is moles over liters. So our liters cancel out and we are left with moles. So this will give us 0.000106. Essentially, it's just adding a few zeros. So at this point, we have the number of moles of C2O4 that exist inside this Erlenmeyer flask that we are about to titrate. What is going on now is when we do titrate, we say for every 5 Na2C2O4, we have 2 KMnO4 reacting. This is important because this is going to allow us to do our final calculation to actually determine the number of moles that have reacted. The idea here is this 48.36 milliliters means that at this point, the number of moles of KMnO4 and the number of moles of C2O4 are equivalent. That would be considered the end point of this titration, and it occurs at this 48.36 milliliter volume. So that would mean that at this point, KMnO4 equals Na2C2O4. Usually this is indicated by a color change in the solution because in this case, we are actually using an indicator of KMnO4, which will undergo that color change. So Our final step is to determine, or not really our final step, we have two more steps. We are going to determine the moles of KMnO4 by saying we have 1.063 times 10 to the negative fourth. I just turned that into scientific notation. Moles, C2O4. Now we are going to do our change from 5 moles of C2O4, 3 moles KMnO4. So 3/5 is going to be being multiplied by, and we will get a value of 4.253 times 10 to the negative fifth moles of KMnO4. So now we know how many moles of KMnO4 reacted with the C2O4. And we also know the volume of that KMnO4 that reacted. And so by using those two factors, we could determine the concentration, because the concentration of KMnO4 equivalent to 4.253 10 to the negative fifth moles over 0.04836 liters. And I got that from my initial problem. 48.36 milliliters is equivalent to 0.04836 liters. So we need to convert that to liters. So this is the final part. We just punched that into our calculator, and we should get 8.794 times 10 to the negative fourth molar of KMnO4. So at this point, we have the concentration of our standard solution. So we could use this solution now for numerous things. And a lab may have standard solutions already pre-prepared that we may dilute to a final concentration, or we may prepare those solutions from stock, as we just did right here. The idea now is, as an analytical chemist, you would be given a sample of perhaps a known substance, and you would be tasked with determining the, for instance, perhaps the concentration of that substance. So let's say we wanted to perform an analysis of calcium with 8.794 times 10 to the negative fourth molar KMnO4. Notice how that is the same concentration of the standard that we created. We are going to use our previously created standard to run this analysis. So let's perform a let me write out the equation of what's going to be. So let's say we have calcium, and it is going to react C2O4, and this is going to generate calcium C2O4, and there's going to be some waters of hydration on it. Going to be aqueous. Plus 2 minus. Okay, so the idea here is we need to take a some unknown unknown containing calcium. Reacts with so we are reacting the calcium with the C2O4. When we do that, we will get a solid precipitate form. What we will do is this solid will be washed with cold water. To remove trace or excess C2O4. What we will then do is redissolve in an acidic solution. So what's going to happen is solid CaC2O4 can't exist as a solid in the acidic solution, and it's going to break apart back into Ca plus 2 plus and C2O4 2 minus. And what's going to happen is we could then titrate with KMnO4. So the KMnO4 is going to react with the C2O4 as it did previously, and we're going to determine the concentration of the C2O4 now. And the C2O4 is going to equal the concentration of the calcium. So let's say this solution was titrated to an endpoint with 16.17 milliliters of KMNO. What is the concentration of calcium? So how will we do this? So let's start with our volume. We know that we have 0.01617 liters of KMnO4 being. We also know that the concentration of KMnO4 is 8.794 times 10 to the negative fourth molar KMnO4. So remember, molar is nothing more than moles over liters. And as a result, we just cancel those liters out and it leaves us with moles. And as a result, we will get 0.0000355 moles of KMnO4. So at this point, we have, whoops, wrong number. That's the next equation. 1.422 times 10 to the negative moles of KMnO4. At this point, these are the moles of KMnO4 we have inside that 16.7 mils that we use. Remember, though, it's not a 1-to-1 reaction. It's a 5-to-2. So for that 1.422 10 to the negative fifth moles of KMnO4, we have 5 moles of C2O4 reacting with 2 moles of MnO4. And so there's that 5-to-2 ratio. Remember, since we're going from KMnO4, KMnO4 will be on the bottom. I probably should just put so we have MnO4 and MnO4 canceling, giving us C2O4, which will give us a mole number of 0.00055 moles. I did not put information in. 2, 3, 4. 3.55 times fifth. All right. Here is the what to do. So these are the number of the moles of KMnO4 that are present in our sample. And let's say that the original sample was 5 milliliters. So let's say I took 5 milliliters of a sample, and that 5 milliliters is what I reacted with the C2O4 to produce the CaC2O4. And then I took that solid that was washed, and then I titrated, or I put it in an acidic solution, and then titrated it. So the original sample was 5 milliliters. What that says is, if I take this 3.55 times 10 to the negative fifth moles of K2O4, and I divide it by 0.005 liters, it would mean that my original sample contained 0.00711 molar Ca. That's the concentration of Ca sample I analyzed. This is essentially the same process you'll do with everything that you titrate. You just find the ratio, and that ratio is honestly the only thing that'll be different in this process. Other than that, you follow this exact same process. Sometimes we will be taking aliquots of a standard like we did here, or a aliquot of a sample, for instance, might also be a thing. But just remember to go back and undilute that aliquot if you need to. So this is titrations of one compound. Let's say that we had a titration of a mixture. So let's say I had Na2CO3 and NaHCO3. So I had both of these inside of a solution. So how would I determine the amount of each of these after a titration? This is what we are going to be figuring out how to do. So let's say that we will titrate the solution with HCl. Let's see how HCl reacts. So we have Na2CO3 plus 2HCl yields 2NaCl plus H2O plus CO2. And if we take NaHCO3, you'll have only one HCl react with it. And this will also yield 2 NaCl plus H2O CO. All right, so the idea here is we have a one and 1 to 2 and 1 to 1. So we have a 1 to 2 and a 1 to 1 ratio going on here. And let's say combined mass of Na2CO3 plus NaHCO3 equals 1.372 grams. Let's say that when I titrated it, I used 29.11 milliliters of 0.7344 molar HCl. So I use these many milliliters of this concentration of HCl to titrate 1.372 grams of Na2CO3 plus NaHCO3. I don't know how much of each one there is, but the combined sample is 1.372. So what we're going to do is we are going to do a little bit of algebra, And we are going to come up with a function or a basic general solution that will allow us to solve these types of compounds or problems. So let's say the grams of Na2CO3 are equal to X, and the grams of NaHCO3 are equal to 1.372 minus X. Sort of makes sense here, because if we subtract this amount from the total amount, we should get this amount, right? So we're going to use this general idea right here. Let's do another thing right here. Let's say that the moles of Na2CO3 are equal to X divided by 105.99, because this is essentially the molar mass of Na2CO3. And let's in the same way say that the moles of NaHCO3 are equal to 1.372 minus X over 84.01 grams. There, we'll leave it like that. So we have the moles of this, and we have the moles of this worked out. Let's move on, and let's actually find out the moles of the HCl that was used in this reaction. So we say that 0.02911 liters of the 0.7344 molar HCl. And what's this going to give us? This is going to, well, again, remember molar, nothing more than moles, liters. So we can cancel out our liters. Liters gives us moles. So that would mean that we have 0.02138 moles of HCl. That would mean these many moles of HCl reacted with this 1.372 grams of this combined sodium carbonate plus sodium bicarbonate. So what the idea now is, we could do one step further. We could say that 2 moles of Na2CO3 plus 1 mole NaHCO3 is equal to 0.02138 moles. So we have the total moles of HCl here. So the total moles of the NaHCO3 plus the Na2CO3 should equal the combined moles of the HCl. The reason why we have 1 and 2 is, well, look at the reaction. We have a 1-to-2 reaction with the Na2CO3 and a 1-to-1 reaction with the NaHCO3. So the idea here is we are going to combine everything that we have together now into a single equation. Because, look, we have the moles of Na2CO3 here and the moles of NaHCO3 here. We have an equation that is equating the moles of Na2CO3 plus the moles of NaHCO3 to the total moles of HCl, which is the amount of everything in the solution. So let's combine these two equations into a single one. So we have 2 times X over 105.99 plus 1.372 minus x all over 84.01, which will equal 0.02138 moles. Now at this point, we could just punch this into a CAS calculator or something like Wolfram Alpha, and we could get ourselves essentially a final solution to this. But instead of doing that, let's say we can't solve let's rewrite everything. Let's say we have a x over c plus b m minus x b equals. So how will we do this? We could say A is the mole ratio of mole ratio A. B is mole ratio B. And what I mean by that is in these reactions that we have right here, we have the 1 to 2 here and a 1 to 1 here. So in the case of our equation here, our A is equal to 2 and our B is equal to 1. So our X is essentially what we want to find out. What is our C? C equals molar mass of A. D equals molar mass of B. M equals total mass. X equals mass of A. And T equals total moles. So you could see T is this, D is this, M is this, X is this. B is a 1 that goes here. X is that. Let's see. A is the 2. And C is that. So we have everything accounted for. And the idea here is we are now going to solve this for X. And I will give you that solution right now because I'm not going to work it out. X equals C. M B minus D T all over C B minus D A. Now this equation is not in your book, or I don't think it's in any book really. But this equation, if you do have it memorized, you will be able to use it to solve for the unknown mass of any a mixture of two things when you titrate. All you need to do now is just plug in those variables into this equation, and you will have the mass of X. And if you have the mass of X, you could find the mass of the other compound by simply performing this 1.372 minus X. And then you will get the mass of NaHCO3. So let's do that right now. Let's plug everything into this equation. We get 105.99 multiplied by 1.372. Subtract 84.01 multiplied by 0.02138. close parentheses. So I have M. B essentially would be multiplied by 1. I have dt all over CB. So C is, again, 105.99. We're going to multiply by 1 minus 84.01 multiplied by 2. And if we punch this into the calculator, we should get a mass of 0.725. So what does that mean? 0.725 equals x. And what does x equal? Well, X is Na2CO3. So if we want to find NaHCO3, so we would take 1.372 minus 0.725. I actually don't have this calculated out, so let me punch this into my calculator really quickly. Two minus 0.725 give us 0.647. So grams of Na2CO3 is equal to 0.725, and grams of NaHCO3 is equal to 0.647. These are the two approaches that you would use to solve for these unknown compounds. And that will pretty much be it for today. So until next time.